Here's a revelation that defies everything we thought possible. Water molecules have been detected in the scorching, chaotic heart of the Milky Way's supermassive black hole, Sagittarius A star. The James Webb Space Telescope caught traces of this water in a region where temperatures routinely exceed millions of degrees, hot enough to vaporize steel. Yet somehow, these molecules endured, clinging to dust grains in a swirling disk of gas and debris orbiting the black hole at fractions of a light-year away. This isn't just a technical glitch in the data, it's a shockwave for astrophysics. How can water, a fragile compound, survive in such a furnace? The answer might rewrite our understanding of black hole ecosystems, revealing hidden chemistry in the universe's most extreme environments. And this discovery? It's just the beginning of a deeper mystery about life's ingredients in the cosmos. The James Webb Space Telescope has revealed a surprising truth about the Milky Way's supermassive black hole. Water can survive in a region far closer to its event horizon than previously thought. This discovery challenges long-held assumptions about the extreme conditions near such a massive gravitational well and offers a glimpse into the complex interplay of heat, pressure, and chemistry in one of the universe's most hostile environments. To understand why this finding is so remarkable, we need to first consider what we know about black holes and the environments they create. At the heart of our galaxy lies Sagittarius A*, a black hole with a mass over 4 million times that of the Sun. Its immense gravity warps spacetime around it, pulling in gas, dust, and even stars that venture too close. As material spirals inward, it forms a swirling accretion disk, heated to millions of degrees by friction and gravitational forces. In this inferno, atoms are stripped of their electrons, and molecules like water should be torn apart by the extreme temperatures. Yet, the James Webb Telescope has detected water in a region of this disk that is much closer to the black hole than scientists had ever anticipated. This finding suggests that the conditions near Sagittarius A* are more nuanced than previously believed, and that water essential to life as we know it might exist in unexpected places within the galaxy. But how did the telescope uncover this? The key lies in the way water interacts with light. Water molecules absorb and emit specific wavelengths of infrared radiation, leaving a unique fingerprint in the spectrum. The James Webb's advanced instruments, designed to peer into the infrared, allowed astronomers to detect these signatures in the glowing gas around Sagittarius A star. The water was found in a region of the accretion disk that is about 700 light-years away from the black hole's event horizon, a distance that, while vast on human scales, is incredibly close in cosmic terms. To put this into perspective, the distance from Earth to the Sun is about 93 million miles, while the region where water was detected is roughly 100 times farther than that. Yet, even at this distance, the environment is extreme. The gas in the accretion disk is heated to temperatures exceeding 1,000,000 degrees, and the gravitational pull of the black hole is so strong that time itself slows down near its edge. Under such conditions, water should be vaporized or dissociated into hydrogen and oxygen. So why does it persist? The answer may lie in the dynamic nature of the accretion disk. While the overall environment is hostile, there are pockets of cooler, denser gas where water can form and remain stable. These regions might be shielded from the full brunt of the heat by magnetic fields or by the presence of heavier elements that radiate excess energy. Additionally, the water detected may not be in liquid form but rather in a vapor state, existing in a delicate balance between evaporation and condensation. The James Webb's observations suggest that the water is not a stable, long-lasting feature but rather a transient phenomenon, created and destroyed in cycles as material flows into the black hole. This raises intriguing questions about the chemistry of extreme environments. If water can exist in such a hostile region, what other molecules might survive? Could there be complex organic compounds forming in the same conditions? These possibilities hint at a deeper complexity in the chemistry of space, where the interplay of heat, pressure, and radiation gives rise to unexpected chemical reactions. The discovery also has implications for our understanding of how black holes interact with their surroundings. While black holes are often seen as destructive forces, they also play a role in shaping the galaxies they inhabit. The energy released as material falls into a black hole can influence the formation of stars and the distribution of matter in its vicinity. If water, and potentially other molecules, can persist in such environments, it suggests that these regions are not as barren as once thought. Instead, they may be dynamic, chemical laboratories where the building blocks of life could, in theory, form under extreme conditions. However, it's important to clarify that this discovery does not imply the presence of life near Sagittarius A star. The water detected is likely part of a vast, diffuse cloud of gas and dust, not a liquid or frozen reservoir. The conditions required for life as we know it, stable temperatures, liquid water, and the presence of organic molecules, are still far from being met in such an environment. Nonetheless, the finding underscores the adaptability of chemical processes in space. It reminds us that the universe is full of surprises, and that even in the most extreme places, the fundamental laws of chemistry can create unexpected phenomena. The James Webb Space Telescope's ability to detect water so close to a black hole is a testament to the power of modern astronomy. By peering into the infrared spectrum, the telescope has opened a new window into the cosmos, revealing details about distant objects and extreme environments that were previously invisible. This discovery is not just about water, it's about the resilience of molecular structures in the face of immense forces. It challenges our assumptions about where and how molecules can exist, and it invites us to rethink the boundaries of what is possible in the universe. As we continue to explore the cosmos, such findings remind us that the universe is not just a vast expanse of empty space, but a complex web of interactions where even the most extreme conditions can give rise to remarkable phenomena. The water near Sagittarius A* is a small but significant piece of this puzzle, offering a glimpse into the intricate dance of matter and energy that defines the universe. The idea that water could exist so close to a supermassive black hole, just a few light-years away from the heart of our galaxy, seems almost fantastical. After all, black holes are regions of space where gravity is so intense that not even light can escape. Yet, scientists have discovered that water molecules can survive in the extreme conditions near Sagittarius A*, the Milky Way's central black hole. How did they uncover this? It began with a tool that has revolutionized our view of the universe, the James Webb Space Telescope. Launched in 2021, the JWST is a marvel of engineering, designed to peer into the cosmos with unprecedented sensitivity. Its primary mission was to study the early universe, but its capabilities extended far beyond that. The telescope's infrared sensors allowed it to detect faint signals from distant stars and gas clouds, including the molecular signatures of water. But to understand how water could exist so close to a black hole, scientists had to look at the environment around Sagittarius A*, a place where temperatures, radiation, and gravitational forces are extreme. For decades, astronomers had theorized that the region near a black hole would be too hostile for water to persist. The intense radiation from the accretion disk, the swirling mass of gas and dust orbiting the black hole, should strip molecules apart, leaving only ionized particles. Yet, the JWST's observations revealed something unexpected: water molecules were not only present but thriving in this hostile environment. The key to this discovery lay in the telescope's ability to analyze light. When light passes through a gas cloud, it interacts with molecules, absorbing specific wavelengths. By studying these absorption patterns, scientists can identify the chemical composition of distant objects. The JWST's advanced spectroscopic instruments allowed researchers to break down the light from the galactic center into its component wavelengths, revealing the presence of water. But this wasn't a simple observation. The region around Sagittarius A* is shrouded in dense clouds of gas and dust, making it difficult to see directly. The JWST's ability to peer through these obscuring layers was critical. Its large mirror and high-resolution instruments enabled it to capture detailed images of the galactic center, even in the presence of thick interstellar material. However, the process of analyzing the data was just as complex. Scientists had to account for the intense radiation from the black hole's accretion disk, which could distort the light and create false signals. They also had to distinguish between water and other molecules that might emit similar spectral signatures. This required sophisticated algorithms and cross-referencing with existing data from other telescopes. The team used a combination of ground-based observatories and space-based instruments to validate their findings. For example, the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile had previously detected molecular gas in the galactic center, but its resolution was limited. The JWST's infrared capabilities provided a clearer picture, allowing scientists to pinpoint the exact location of water molecules. The discovery also relied on long-term observations.
The galactic center is a dynamic region, with gas and dust constantly shifting due to the black hole's gravitational pull.
To capture a stable image, the JWST had to observe the area over an extended period, compiling data from multiple sessions. This process took months of meticulous analysis, as researchers sifted through vast amounts of data to identify patterns consistent with water. The breakthrough came when the team noticed a distinct absorption feature in the infrared spectrum that matched the known signature of water. This was a major finding because it challenged existing models of how matter behaves near black holes. Previously, scientists believed that the extreme temperatures and radiation would prevent water from existing in its molecular form.
The presence of water suggested that the environment was more complex than previously thought. It also raised questions about the mechanisms that allowed water to survive.
One possibility is that the water exists in a region shielded from the most intense radiation, such as within dense clouds of gas or in the cooler outer layers of the accretion disk. Another theory is that the water is part of a larger molecular cloud that has been influenced by the black hole's gravitational forces, creating pockets where molecules can remain intact. These hypotheses are still being tested, but the JWST's observations have provided crucial evidence. The implications of this discovery extend beyond the immediate vicinity of Sagittarius A star. If water can survive in such an extreme environment, it suggests that the conditions for forming complex molecules and perhaps even the building blocks of life might be more widespread in the universe than previously imagined.
This has sparked renewed interest in studying other galactic centers, where similar processes might be occurring. The JWST's role in this discovery underscores the power of modern astronomy. By combining cutting-edge technology with decades of theoretical knowledge, scientists have opened a new chapter in our understanding of the cosmos.
The journey to uncover the presence of water near a black hole was not just about detecting a single molecule.
It was about unraveling the intricate balance of forces that govern the universe.
From the design of the telescope to the analysis of its data, every step required precision, patience, and a willingness to challenge existing assumptions. As researchers continue to study the galactic center, they are likely to uncover more surprises. The story of water near Sagittarius A* is a reminder that the universe is full of mysteries waiting to be explored, and that tools like the James Webb Space Telescope are essential in unlocking them. In the heart of our galaxy, where gravity bends light and time stretches, a discovery has upended our understanding of what's possible in the universe. The James Webb Space Telescope has detected water molecules in the vicinity of Sagittarius A*, the supermassive black hole at the center of the Milky Way. This finding is nothing short of extraordinary because water, as we know it, should not survive in such an extreme environment. The region around a black hole is a cauldron of intense heat, radiation, and gravitational forces, where even the simplest molecules are expected to be torn apart. Yet, here, in the shadow of a black hole millions of times more massive than our Sun, water exists. This chapter explores the science behind this discovery, the implications for our understanding of the cosmos, and why this finding challenges everything we thought we knew about the limits of matter and chemistry in the universe.
To grasp the significance of this discovery, we must first consider the environment surrounding a supermassive black hole. At the core of the Milky Way lies Sagittarius A*, a black hole with a mass equivalent to about 4 million suns. Its gravitational pull is so intense that it warps spacetime around it, creating a region known as the accretion disk, a swirling halo of gas, dust, and ionized particles that spirals inward. As these materials fall toward the event horizon, the point of no return, friction and gravitational forces heat them to temperatures exceeding millions of degrees. In such conditions, water, which boils at just 100 degrees Celsius on Earth, would be vaporized instantly. Yet, the James Webb Telescope has detected molecular water in this hostile realm, suggesting that the presence of water is not just possible, but perhaps even common in these extreme environments. The key to understanding how water can survive near a black hole lies in the physics of the accretion disk. While the innermost regions of the disk are indeed scorching, the outer parts may be cooler, allowing for the existence of complex molecules. However, the detection of water so close to the black hole within a few light-years of the event horizon raises new questions. How can water, which requires liquid water to exist in its familiar form, persist in such a high-energy environment? The answer may lie in the interplay between radiation, temperature gradients, and the unique chemistry of space.
The James Webb Telescope's ability to detect water through its spectral signature, specifically, the way it absorbs and emits infrared light, has revealed that water molecules are not only present but are part of a broader chemical network in the accretion disk. This suggests that the conditions around a black hole are more complex and chemically rich than previously imagined. One possibility is that the water detected is not in its liquid form but exists in a different state, such as ice or in a plasma-like configuration, allowing it to withstand the extreme temperatures. Alternatively, the water may be part of a larger molecular cloud that has been drawn into the accretion disk, where it remains shielded from the most intense radiation.
The accretion disk itself is a dynamic system, with regions of varying density and temperature.
While the innermost parts are dominated by ionized gas and high-energy radiation, the outer regions may harbor cooler, denser material where molecules like water can form and persist. The James Webb Telescope's infrared capabilities have allowed scientists to peer into these regions, revealing that water is not just a fleeting presence but a stable component of the disk's chemistry. This discovery has profound implications for our understanding of astrophysics and the behavior of matter under extreme conditions. For decades, the accretion disk around a black hole has been considered a site of intense destruction, where matter is stripped of its molecular structure and reduced to plasma.
However, the detection of water challenges this view, suggesting that complex molecules can survive in these environments.
This has led scientists to reconsider the chemical processes that occur in the vicinity of black holes.
If water can exist in such a hostile region, what other molecules might be present? Could there be organic compounds, the building blocks of life, thriving in these extreme conditions?
While the presence of water does not necessarily imply the existence of life, it does open the door to new possibilities about the chemistry of space and the potential for life to exist in unexpected places.
Moreover, the detection of water near Sagittarius A* has implications for our understanding of how galaxies evolve.
Supermassive black holes are believed to play a crucial role in shaping the structure of their host galaxies, influencing star formation and regulating the flow of gas and dust. If the accretion disks around these black holes are rich in complex molecules, it could mean that the interplay between black holes and their surroundings is more intricate than previously thought. The presence of water in these regions might also affect the way gas and dust are distributed, influencing the formation of stars and planetary systems. This discovery adds another layer to the complex relationship between black holes and the galaxies they inhabit, highlighting the interconnectedness of cosmic phenomena.
Another angle to consider is the broader context of water in the universe. Water is one of the most abundant molecules in the cosmos, found in comets, asteroids, and the atmospheres of exoplanets. However, its presence in the immediate vicinity of a black hole is still remarkable.
The James Webb Telescope's detection of water near Sagittarius A* suggests that the processes that create and sustain water are more widespread and adaptable than we thought. This could have implications for our search for water and potentially life in other parts of the galaxy.
If water can survive in the extreme conditions around a black hole, it raises the question, where else might water exist in the universe? Could it be found in the shadows of other supermassive black holes, or even in the dense, high-energy environments of neutron stars and pulsars?
The significance of this discovery also lies in its challenge to our assumptions about the limits of matter and chemistry.
For years, scientists have assumed that the extreme conditions near a black hole would prevent the formation of complex molecules.
However, the presence of water in this region suggests that the universe is far more dynamic and chemically diverse than previously believed.
This has sparked renewed interest in studying the chemical composition of accretion disks and the processes that allow molecules to form and persist in such extreme environments.
The James Webb Telescope's ability to detect these molecules in the infrared spectrum has opened a new window into the chemistry of space, revealing that the universe is a far more intricate and interconnected place than we once imagined. In addition to its scientific implications, this discovery has philosophical and existential weight. The idea that water, a molecule essential to life as we know it, can exist in the shadow of a black hole challenges our understanding of the conditions necessary for life. While the presence of water alone does not confirm the existence of life, it does suggest that the ingredients for life may be more widespread in the universe than previously thought. This has sparked discussions about the potential for life to exist in extreme environments, from the depths of the ocean on Earth to the surfaces of icy moons in our solar system and, perhaps, even in the vicinity of black holes. The discovery of water near Sagittarius A** is a reminder that the universe is full of surprises, and that our search for life and understanding of the cosmos is far from complete. Finally, this discovery underscores the importance of advanced technology in expanding our knowledge of the universe. The James Webb Space Telescope, with its unprecedented sensitivity and ability to peer into the infrared spectrum, has allowed scientists to detect molecules that were previously beyond our reach. This highlights the role of innovation in science and the power of observation in uncovering the mysteries of the cosmos. As we continue to refine our instruments and techniques, we may uncover even more surprises: water in the atmospheres of distant exoplanets, complex organic molecules in the interstellar medium, or even signs of life in the most unlikely places. The universe is vast, and our understanding of it is still in its infancy. Each new discovery brings us closer to unraveling its secrets, and the detection of water near Sagittarius A* is a testament to the enduring curiosity and ingenuity of scientists. In conclusion, the detection of water near the Milky Way supermassive black hole is more than just a scientific curiosity. It is a profound reminder of the complexity and diversity of the universe. It challenges our assumptions about the limits of matter and chemistry, opens new avenues for research, and deepens our understanding of the interconnectedness of cosmic phenomena. As we continue to explore the cosmos, discoveries like this will undoubtedly shape our view of the universe, revealing that even in the most extreme environments, the building blocks of life may persist. The James Webb Space Telescope has given us a glimpse into this reality, and it is only the beginning of a much larger story, one that continues to unfold as we look beyond the stars. For centuries, the idea of black holes was more philosophy than science. Ancient astronomers speculated about dark voids in the cosmos, but it wasn't until the early 20th century that Einstein's theory of general relativity provided a mathematical framework for their existence. By the 1960s, scientists like Subrahmanyan Chandrasekhar and John Wheeler began to flesh out the concept of singularities, regions of space where gravity becomes so intense that not even light can escape. Yet, these were still theoretical constructs. It wasn't until the 1970s, with the discovery of quasars and the first hints of supermassive black holes at the centers of galaxies, that the idea of these cosmic monsters began to take shape. The Milky Way's own supermassive black hole, Sagittarius A*, was identified in the 1990s through observations of stars orbiting it at extreme speeds, a breakthrough that confirmed its existence and mass. But even as scientists began to map the galaxy's central region, they faced a fundamental challenge: how to peer into the extreme environment around a black hole, where gravity and radiation dominate. For decades, the answer lay in the development of increasingly sophisticated telescopes, each peeling back a layer of mystery. The Hubble Space Telescope, launched in 1990, revolutionized our view of the universe by capturing crisp images in visible light, but it couldn't penetrate the dense clouds of dust and gas that obscured the galactic center. The solution came in the form of X-ray telescopes, like the Chandra X-ray Observatory, which could detect the high-energy emissions from the superheated gas swirling around black holes. These observations revealed the violent, chaotic dance of matter in the accretion disks, but they also raised new questions. What happens to molecules like water in such extreme conditions? Could they survive the scorching temperatures and radiation? For years, the answer remained elusive. The problem was that water, a molecule made of hydrogen and oxygen, requires a delicate balance of temperature and pressure to exist in its liquid form. In the vicinity of a supermassive black hole, temperatures can reach millions of degrees, and the intense radiation from the accretion disk would likely break apart any water molecules. Yet, astronomers had long known that water exists in the universe, in star-forming regions, in comets, and even in the atmospheres of exoplanets. The question was whether it could persist in the hostile environment near a black hole. Early studies of the Milky Way's galactic center focused on the interplay between the black hole's gravity and the surrounding gas. Observations from the Spitzer Space Telescope in the 2000s, which operated in the infrared range, hinted at the presence of complex molecules, including water, in the dusty clouds orbiting Sagittarius A star. But these findings were indirect, relying on the detection of spectral signatures rather than direct imaging. The limitations of these instruments meant that scientists could only infer the presence of water, not confirm its survival in the extreme conditions near the black hole. The breakthrough came with the James Webb Space Telescope, launched in 2021. Unlike its predecessors, JWST is designed to observe in the infrared, or it can peer through the dust that has long blocked our view of the galactic center. Its advanced instruments, including the mid-infrared instrument, MIRI, allowed astronomers to detect the faint, telltale signatures of water molecules in the region around Sagittarius A star. This discovery was not just about confirming the presence of water, it was about challenging our assumptions about the limits of molecular survival in extreme environments. For decades, scientists had thought that the intense radiation and temperatures near a black hole would make such survival impossible. Yet, the JWST's findings suggest that water can exist in a form that is stable enough to persist despite the harsh conditions. This raises profound questions about the physics of extreme environments and the resilience of molecules in the cosmos. But to fully appreciate the significance of this discovery, we need to look back at the long history of how we've come to understand black holes and their environments. The journey began with the theoretical predictions of Einstein and the observational breakthroughs of the 20th century. It continued through the development of radio astronomy, which allowed scientists to map the structure of the galactic center and detect the motion of stars around Sagittarius A star. These observations confirmed the black hole's existence and provided critical data on its mass and behavior. Yet, even as these discoveries unfolded, the challenge of observing the galactic center remained. The region is shrouded in thick clouds of interstellar dust, which absorb visible light but allow infrared radiation to pass through. This is where the Spitzer and later the James Webb Space Telescopes played a crucial role. Their ability to observe in the infrared range has transformed our understanding of the galactic center, revealing complex chemistry in the gas and dust that surrounds the black hole. These observations have shown that the environment near Sagittarius A* is far more dynamic than previously thought. It is a region of intense activity, where gas is funneled into the accretion disk, where magnetic fields play a critical role in shaping the flow of material, and where the interplay between radiation and matter creates a complex web of physical processes. The discovery of water in this region adds another layer to this picture. It suggests that the galactic center is not just a site of destruction but also a place where complex molecules can form and persist. This challenges the notion that the extreme conditions near a black hole are inhospitable to all forms of matter. Instead, it points to a more nuanced understanding of how physical and chemical processes operate in such environments. The implications of this discovery extend beyond the Milky Way. Water is a key ingredient for life as we know it, and its presence in the galactic center raises intriguing questions about the potential for life in the universe. While the conditions near a supermassive black hole are extreme, the discovery of water in such a location suggests that the universe is far more chemically diverse than we once believed. It also highlights the importance of continued exploration of the galactic center, a region that has long been a focal point for astrophysical research. The JWST's findings are a testament to the power of modern observational technology and the patience of scientists who have spent decades unraveling the mysteries of the cosmos. But they also remind us that our understanding of the universe is constantly evolving. Each new discovery builds on the foundations laid by earlier missions and theories, pushing the boundaries of what we thought possible. The story of water near Sagittarius A* is not just about a single molecule, it is about the broader quest to understand the extremes of the universe and the resilience of matter in the face of unimaginable forces. As we continue to explore the cosmos, we are reminded that the universe is full of surprises, and that the search for knowledge is as much about asking the right questions as it is about finding the answers. The James Webb Space Telescope has revealed a startling truth about the Milky Way's supermassive black hole, Sagittarius A star. Water, in the form of vapor, has been detected in the accretion disk surrounding this cosmic behemoth, a region where temperatures should be so extreme that any liquid or solid form of water would be obliterated. This discovery challenges long-held assumptions about the limits of molecular survival in extreme environments. But it also raises a host of unanswered questions. How can water persist in such a hostile zone? What does this mean for our understanding of black hole ecosystems? And what other mysteries might this finding unlock? Let's explore the scientific debates and unresolved enigmas that this discovery has sparked. One of the most immediate mysteries is the very survival of water in the accretion disk. The region around a supermassive black hole is a furnace of intense radiation and gravitational forces. The accretion disk, a swirling mass of gas and dust spiraling toward the event horizon, reaches temperatures in the millions of degrees. Under such conditions, water molecules should be torn apart by high-energy photons and stripped of their electrons. Yet, the James Webb Space Telescope has detected spectral signatures consistent with water vapor in this environment. How is this possible? Scientists are now grappling with the possibility that water exists in a different form or that the conditions in certain parts of the disk are more hospitable than previously thought. A leading hypothesis is that water might exist in a region of the accretion disk where the balance between radiation and temperature allows it to persist. The disk is not a uniform structure, it has complex layers and varying densities. In some areas, the gas might be cooler or shielded from the most intense radiation, creating pockets where water can condense and remain stable. However, even in these regions, the temperatures would still be far above the boiling point of water. This suggests that the water detected might not be in a liquid or solid state but rather in a vapor form that exists in equilibrium with other molecules. The exact mechanisms that allow this equilibrium to form are still under investigation. Another layer of complexity arises from the role of magnetic fields in the accretion disk. These fields can influence the flow of gas and the distribution of energy within the disk. Some researchers propose that magnetic forces might create regions where the gas cools sufficiently to allow water vapor to condense. However, the interplay between magnetic fields, radiation, and thermal dynamics is not yet fully understood. The James Webb Space Telescope's ability to peer into these regions has provided new data, but the interpretation of these data remains a topic of debate. For instance, the spectral signatures detected could be influenced by other molecules, such as carbon monoxide or hydroxyl radicals, which share similar absorption patterns. Distinguishing between these possibilities requires further analysis and cross-referencing with other observational data. The discovery also has profound implications for our understanding of planet formation in extreme environments. If water can exist in the vicinity of a supermassive black hole, what does that mean for the potential of life-supporting conditions in such regions? While the accretion disk itself is unlikely to host planets, the presence of water suggests that the materials necessary for planet formation might be more widespread than previously thought. In the broader context of the galaxy, water is a key component in the formation of rocky planets and the development of complex chemistry. If such materials can survive in the extreme conditions near a black hole, it raises questions about the distribution of elements across the galaxy and the potential for life in unexpected places. Yet, the detection of water near Sagittarius A* is not without its challenges. The James Webb Space Telescope's instruments are designed to detect faint signals against the backdrop of intense cosmic radiation, but even the most advanced technology has its limits. The spectral signatures of water vapor must be carefully separated from other emissions, such as those from ionized gas or dust. Some scientists argue that the observed water signal could be a result of contamination from nearby regions of the disk or from the interstellar medium. This highlights the need for additional observations using different wavelengths or complementary instruments to confirm the findings. For example, future missions equipped with high-resolution spectroscopy could provide more precise data, helping to distinguish between water and other molecules. Moreover, the discovery has sparked broader questions about the nature of black hole environments. Supermassive black holes are not just gravitational monsters, they are also sources of intense energy, emitting radiation across the electromagnetic spectrum. The presence of water in such a region suggests that the physical processes governing these environments are more complex than previously assumed. For instance, the interaction between radiation, magnetic fields, and gas dynamics might create conditions where certain molecules can persist despite the extreme conditions. Understanding these processes could shed light on how black holes influence their surroundings and how they contribute to the evolution of galaxies. Another intriguing mystery is the potential for water to exist in other forms. While the James Webb Space Telescope detected water vapor, it's possible that ice or other exotic phases of water might also be present. In the cold, dense regions of the accretion disk, water could condense into ice, which might then be incorporated into larger structures like comets or icy bodies. However, the extreme temperatures near the black hole would likely prevent the formation of stable ice. This raises the question, how do these materials move through the disk, and what role do they play in the overall dynamics of the system? The answers to these questions could provide insights into the transport of material in accretion disks and the potential for the formation of complex molecules in such environments. The implications of this discovery also extend to our understanding of the universe's chemical composition. Water is one of the most abundant molecules in the cosmos, but its presence near a supermassive black hole suggests that it might be more widespread than previously thought. This could have significant consequences for our models of galaxy formation and evolution. If water can survive in such extreme conditions, it might mean that the materials necessary for life are more readily available across the universe. However, this also raises questions about the role of black holes in distributing these materials. Are they sources of heavy elements, or do they act as barriers to their spread? These are questions that remain at the forefront of astrophysical research. In addition to these scientific questions, the discovery has sparked philosophical and existential reflections. The idea that water, a molecule essential to life as we know it, can exist in such an extreme environment challenges our assumptions about where life might exist. While the conditions near a supermassive black hole are far from hospitable, the presence of water suggests that the building blocks of life might be more ubiquitous than we imagined. This has implications for the search for extraterrestrial life, as it expands the range of environments where such materials could be found. However, it also underscores the vast unknowns that still lie beyond our current understanding. As scientists continue to analyze the data from the James Webb Space Telescope, they are uncovering new layers of complexity in the universe. The detection of water near Sagittarius A* is not just a breakthrough in observational astronomy, it is a catalyst for deeper inquiry into the fundamental processes that govern the cosmos. Each new finding brings with it a cascade of questions, from the mechanics of molecular survival in extreme environments to the broader implications for the distribution of elements and the potential for life. These mysteries are not just scientific puzzles, they are invitations to explore the vast, uncharted territories of the universe. And as we peer deeper into the cosmos, we are reminded that the universe is far more intricate and mysterious than we ever imagined. As we stand on the edge of a new era in astrophysics, the James Webb Space Telescope's discovery that water can survive so close to the Milky Way's supermassive black hole has opened a door to questions that demand answers. What does this mean for our understanding of extreme environments? How do these molecules endure in conditions that should tear them apart? And what other mysteries might lie hidden in the same cosmic neighborhood? The next few years will see a flurry of scientific efforts to probe these questions, driven by cutting-edge instruments, ambitious space missions, and the relentless curiosity of researchers. Let's explore the path ahead, what's coming next in the quest to unravel the secrets of water near the black hole, and how these discoveries might reshape our view of the universe. The first step in this journey is to look closer at the tools already in motion. The James Webb Space Telescope, which made this groundbreaking discovery, is far from finished. Its instruments, particularly the near-infrared spectrograph (NIR-SPEC) and the mid-infrared instrument (MIRI), are designed to capture detailed spectra of distant objects, and they've already proven their worth in detecting molecular signatures. But JWST's capabilities are limited by its distance from Earth and the constraints of its orbit. Future observations with JWST will focus on refining these measurements, searching for subtle variations in the water's composition or detecting other molecules that might coexist in this extreme environment. For instance, scientists are eager to determine whether the water is in vapor form, bound in ice, or part of a complex molecular network. If JWST can detect traces of oxygen or hydrogen alongside water, it might hint at the presence of more complex chemistry, potentially even the building blocks of life. However, JWST's reach has its limits, and its ability to peer deeper into the heart of the black hole's vicinity will depend on the patience of astronomers and the patience of the telescope itself. As we wait for more data, other observatories are stepping into the spotlight. One of the most anticipated projects in the coming decade is the Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of Chile. With a primary mirror spanning 39 meters, nearly the length of a football field, the ELT will be the largest optical telescope ever built. Its advanced adaptive optics system will allow it to pierce through Earth's turbulent atmosphere, capturing images with unprecedented clarity. While the ELT is primarily designed to study exoplanets and distant galaxies, its ability to observe in the visible and near-infrared spectrum could provide critical insights into the environment around the Milky Way's black hole. By analyzing the light emitted by the accretion disk, the swirling mass of gas and dust that orbits the black hole, scientists might uncover details about the temperature, density, and chemical composition of this region. If the ELT can detect variations in the disk's structure, it could help explain how water molecules are able to persist in such a hostile environment. For example, if the disk contains pockets of cooler gas or regions shielded from the black hole's intense radiation, these could serve as sanctuaries for water. The ELT's observations might also reveal whether the water is part of a broader network of molecules, such as carbon monoxide or methane, which could provide clues about the chemical processes at play. Another key player in this scientific race is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. Named after the former NASA deputy administrator, this telescope is a successor to the Hubble Space Telescope and is designed for wide-field surveys that can capture vast swaths of the universe in a single image. Its primary mission includes mapping dark matter and studying the expansion of the universe, but its capabilities extend far beyond these goals. The Roman telescope's advanced coronagraphs and high-resolution cameras will allow it to detect faint signals from distant objects, including the faint glow of water molecules near the black hole. By combining data from Roman with existing observations from JWST, scientists could create a more comprehensive picture of the black hole's surroundings. For instance, Roman's ability to observe in the near-infrared spectrum could help distinguish between different types of molecular emissions, such as those from water versus other compounds. This distinction is crucial because it would help determine whether the water is a transient phenomenon or part of a stable, long-term reservoir. Moreover, Roman's wide-field surveys might reveal other regions of the galaxy where similar conditions exist, offering a broader context for the black hole's unique environment. Looking further ahead, the next generation of space telescopes, such as the proposed LUVOIR, Large UV Optical Infrared Surveyor, and HABEX, Habitable Exoplanets Observatory, could revolutionize our understanding of water near black holes. These missions, though still in the planning stages, are designed to push the boundaries of what we can observe in the universe. LUVOIR, for example, would be capable of observing in the ultraviolet and visible spectrum, providing data that complements JWST's infrared observations. This multi-wavelength approach could help scientists piece together a more complete picture of the black hole's environment. If LUVOIR can detect the faint glow of water molecules in the ultraviolet, it might reveal how they interact with high-energy radiation from the black hole. Similarly, HABEX's focus on exoplanets and their atmospheres could inspire new methods for studying the chemistry of distant systems, including those near supermassive black holes. While these missions are not yet operational, their development is already shaping the future of astrophysics, and their potential to answer questions about water near black holes is immense. Beyond space-based observatories, ground-based facilities are also playing a critical role in this scientific endeavor. The Event Horizon Telescope, EHT, which famously captured the first image of a black hole's event horizon, is another key player. The EHT's high-resolution imaging capabilities have already provided groundbreaking insights into the structure of the Milky Way's black hole, and future observations could build on this foundation. By combining EHT's data with JWST's spectroscopic findings, scientists might uncover details about the accretion disk's dynamics. For instance, if the EHT can resolve the temperature gradients within the disk, it could help explain how water molecules are able to survive in such extreme conditions. The EHT's observations might also reveal whether the disk contains regions with sufficient cooling to allow water to exist in vapor form, or if the water is locked in ice beneath a layer of gas. These insights would not only shed light on the black hole's environment but also provide a deeper understanding of how matter behaves in the vicinity of such massive objects. However, the journey to confirm and extend these findings is not without challenges. One of the biggest hurdles is the sheer complexity of the environment near a supermassive black hole. The region is subject to extreme gravitational forces, intense radiation, and violent turbulence, all of which could affect the survival of water molecules. Future observations must account for these variables, and any discrepancies between theoretical models and actual data could lead to new discoveries. For example, if future missions find that water is not as abundant as initially thought, it might challenge existing theories about the chemical processes in these regions. Alternatively, the detection of other molecules, such as oxygen or carbon dioxide, could indicate the presence of more complex chemistry, potentially even the seeds of life in these extreme environments. These possibilities underscore the importance of continued observation and the need for a diverse array of instruments to tackle the question from multiple angles.
In addition to confirming the initial findings, future missions may also explore the broader implications of water near black holes. For instance, if water can survive so close to a supermassive black hole, what does that mean for the distribution of water in the galaxy? Could similar conditions exist around other black holes, and if so, what does that imply about the chemical evolution of galaxies?
These questions are not only scientifically intriguing but also have profound implications for our understanding of the universe's history and its potential for life. By studying the chemistry of these extreme environments, scientists might uncover new pathways for the formation of complex molecules, which could have applications beyond astrophysics, such as in materials science or astrobiology. As we look to the future, it's clear that the quest to understand water near the Milky Way's supermassive black hole is far from over. The next few years will bring a wave of new observations, technological advancements, and scientific breakthroughs that could reshape our understanding of this phenomenon. From the continued operations of the James Webb Space Telescope to the upcoming missions of the Extremely Large Telescope and the Nancy Grace Roman Space Telescope, each step forward brings us closer to answering the questions that have captivated astronomers for decades. The journey ahead is as much about the tools we use to observe the universe as it is about the mysteries we seek to uncover. And as we peer deeper into the cosmos, one thing is certain: the universe continues to surprise us, and the answers we find may challenge everything we thought we knew about the survival of water and life in the most extreme environments imaginable. Water can survive surprisingly close to the Milky Way's supermassive black hole. James Webb Space Telescope finds this part of our deep dive into water can survive surprisingly close to the Milky Way's supermassive black hole. James Webb Space Telescope finds focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.